This is the project presentation for Group 10, consisting of Marc Eder, Jeff Craley, Joe Raser, Fanghui Zhang, and Matthew Kidd. Our project was to implement a storage locker that uses deduplication. What is deduplication? Well, deduplication's goal is to drastically reduce the storage space requirements needed to store multiple files by storing the file redundancies as few times as possible. We will talk about our approaches and methods that we use to do this over the next 9.5 minutes. If you have any questions, feel free to ask us during our live demonstration in class this Thursday. The deduplication storage system. In a storage locker, we keep track of all the files that have been added to the locker in a file list, as well as a dictionary containing all the unique contents of chunks of files that have been added. We also keep track of locker name as a unique identifier, as well as the size of any given locker. In our file list, we actually keep track of certain information from each file. We keep track of the file name, its index in the storage locker, its size, the chunk size that was used to process the file, as well as a hash of the entire file. Most importantly, we actually keep track of what we call a file reconstructor, which is a list of keys from our dictionary ordered in such a way that we can iterate through it to reconstruct and regenerate our file. Additionally, we store a Bloom filter for each file to keep track of the dictionary keys that need to be used in order to regenerate the file. This comes in handy during deletion, which we'll talk about later in the presentation. Inserting a file. When a file has been selected to be inserted into our locker, the first step that needs to be taken is to break it up into blocks of content that we call chunks. There are two methods for chunking a file. The first is called fixed block chunking. In fixed block chunking, we determine a certain block size, and then we break the file into chunks of that given block size. This approach is very fast, as you don't need to examine the content being read in. Instead, when a certain number of bytes has been read, you mark the end of a chunk, you hash it and store that key value pair, the hash and the chunk, in your dictionary. However, this approach is not very good for insertion and deletion edits. Only for character modification. The reason for this is by inserting or deleting a character, you are now offsetting every subsequent character. What this leads to happening is that future chunks, even though they may only differ from an existing chunk by one character, they are now read in as an entirely new chunk. This leads to redundancy in your data storage. So while this method is very fast, you're trading off storage space. A more robust approach is what's called dynamic chunking. In dynamic chunking, we search for a certain characteristic of the text that we are reading in order to delineate the beginning and the end of the chunk. In order to do this, we use what's called a polynomial hash, and we look for what is called the Rabin fingerprint. This approach allows us to handle any kind of modification to a file, because any insertions or deletions that might affect one chunk will at most affect the subsequent chunk, but will not propagate through to all future chunks afterwards in the way that fixed size chunking does. The major drawback of dynamic chunking, however, is that it slows down the processing speed as you are forced to read through all the content in order to delineate the chunks. Nevertheless, if your goal is to reduce redundant storage, dynamic chunking is generally the way to go. Once the file has been broken into chunks, these chunks are stored in our locker in three ways. The first is in a hash map that we call the dictionary. Each chunk is stored in the dictionary as a key value pair, where the value is the content of the chunk itself, and the key is the MD5 hash of that content. Additionally, for each file, we reference this dictionary with two different data structures. The first is an array list that we call the file reconstructor. As chunks from a file are being added in order, their references are being added to this array list. This is then used later on for retrieval, which we'll talk about in just a minute. Additionally, these references are added to a Bloom filter. This Bloom filter comes in handy in deletion, which we'll get to later in the presentation. Our method of file insertion actually makes file retrieval very easy. For all our locker needs to do to retrieve a file is to access that file's file reconstructor array list and iterate through the keys in it. For each of those keys, we access the value in the dictionary, which is the contents of our chunks. We then take those chunks and we write them in order to a file. The locker then outputs that file as a copy of the original, and our file has been retrieved.
When a file is deleted from the locker, any chunk inside that file that is not used in any other file should be removed from the dictionary. Naive methods of checking whether a given chunk is present in another file can be very inefficient, both in terms of time and space. For example, scanning through every file for the presence of a given chunk can take a lot of time. On the other hand, keeping a list of every chunk in a given file is inefficient in terms of space. Our solution was to use a bloom filter. For each file, a bloom filter was created and stored in the locker alongside that file. When a file is to be deleted, all of the chunks inside that file are checked against all of the other files' bloom filters. If we find that a chunk is not being used in another file, we know that it's okay to delete. Because we are using a bloom filter, it is possible that we may return false positives for some given chunks, meaning that chunks that are okay to be deleted will not be. This probability had to be balanced by the length of the bloom filter in order to ensure that the space required to store each bloom filter did not take up too much space to make deletion impractical, even if there were false positives. To give a user different options for running our duplicator in a local environment, we implemented a GUI, a command line text-based interface, and an argument parser for command line launches. The GUI allows the user to easily access the locker of their choosing and add, retrieve, and delete files. A text-based command line interface is also available. While the GUI provides a more intuitive user experience, the text-based interface provides more detail regarding space and storage for any individual file or locker. A user can also use the command line to run a single command. An argument string can be appended to the program call. In this case, the text-based interface will not be initiated, and the specified action will be taken directly. This allows a user who wishes to quickly add, retrieve, or delete files from the command line directly the ability to do so efficiently.
For our data deduplication, we implemented networked access through a client and server side socket setup. The server side creates a socket and then a input and output stream. Server side prompts the client, once a connection has been made, to either create or open an existing locker. Client side connects to the server through a GUI by prompting for the IP address. It then opens the connection and either creates a new locker or opens an existing one. The client is then able to retrieve, input a file on the server side, or store a file. Moving forward, we'd like to implement the passing file from the client to the server and vice versa.
So we tested our deduplication performance on 3 different file types. We used text files, JPEG images, and then bitmap images. We generated similar files with random changes at different rates. We used character edits and deletions for text files and just random pixel changes for the images. We also varied the file size and the average chunk size, and we iterated through all these variables to pick the best chunk size and to see the limitations of our program. So this is a plot of the deduplication rate versus the character edit and deletion rate. On the x-axis is the deduplication rate. Obviously, the higher that rate, the better the performance. On the x-axis is the edit and deletion rate, all the way from a 1 in a million chance on the far left down to a 1 in 10,000 chance of a character edit or deletion, all the way towards the right. And as you can see, the different chunk sizes we tested are in probably in different colors. The red is the half a kilobyte, and then the pink, all the way up to the pink, which is the 8 kilobytes. And we ended up going with the 8 kilobyte chunk size because, as you can see all the way on the left-hand side here, it performed well in the low edit and deletion rate regime, which is sort of what was laid out in the parameters of this project and the minimum requirements, and it was the fastest because you have to do less of the deduplication steps. Now, of course, as you get to a higher and higher error rate, you can see, look at the pink circles as you move to the right in the graph. You can tell that the performance goes down significantly once we start moving out of that low probability of a character changing or being deleted. And so, if we anticipated using this software for files with that sort of probability of character edit, then it would make sense to move more towards smaller chunk sizes like a kilobyte or less. But we chose to sort of optimize this for speed over more error-prone files.